Hi sir and classmates. Our title of our chapter is Traps, Dynamics, and Dasies. And we are Group 9. Our group members is Camerino, Aira, Merielyne G, Dauplo, Gerald Jr, David, Karylle, Irish, Postrado, Gerie, Maureen. And our introduction is the ninth chapter of Ian Stewart Nature's Number talks about the numerical patterns around the environment and how it's perceived, different between genetics and mathematicians, as nature looks complex as everybody thinks. It's actually simple as it seems. In our main body, water drop studies have been through many shelves of books about the shapes of teardrop. Many thought of the teardrop as somewhat of a semicircular shape with a point on one end, but it's actually not. Theoretically, this is what most physicists and mathematicians thought of the shape of a teardrop. However, it was falsified by a physicist named Lord Rayleigh, who drew it on early literature. Howell Peregrine. Howell is a British mathematician at Bristol University. His main contribution was mainly fluid mechanics, including free surface flows like water waves and causal engineering. One of his contributions was in 1990, identifying the real shape of the water drop with the help of his colleagues. He identified this discovery as complex but interesting. Illustration of the water droplet. The formation of the droplet begins with a detachment hanging slowly, developing a curve, waist which narrows as it falls. As the droplet falls away, it pulsates for a while, then turns into a spear. The thread meets this spear until it turns into a sharp point. The thread starts to narrow and detaches. As it falls, the ends round off and the series of waves travels along it. And finally, the sharp end of the top end, and it too detaches. As it falls, its top end rounds off, and a complicated series of waves travels along it.
Stimulated ecology. Stimulated ecology or population dynamics. These talk about how change of population are represented by differential equation. Stewart's best example for this is the pig and turtle system because of how pigs are able to find turtles to their snouts. In the real world, there are another kinds of effects that govern the population size, such as random event and variability. The study of Warwick University professors. In 1994, three professors, namely Jackie McLeod, David Grant, and Howard Wilson, made a study that correlates with biological realistic models. Population dynamics models such as the pig and turtle system, the traditional equation. Their study involved making a computer simulation of a large number of agents, interacting according to biological rules. In short, they made a short mathematical computer game. The mathematical game simulation. The game was divided into squares, assigning colors, such as red for a fox, green for a grass, gray for a rabbit, black for a bear, rock. Rules for the simulation. The rules were as simple as it gets. If a rabbit next to grass, it moves to the position of the grass and eats it. If a fox is next to rabbit, it's moved to the position of the rabbit and eat it. At each stage of the game, a rabbit breeds new rabbit with the same chosen probability, a fox that has not eaten for the certain number of the movements. Results. Because of these rules, this gave a simulation that created a so-called artificial ecology, where the foxes and rabbits move at a random rate, and thus creating an ecosystem. When the fox goes near the rabbit, rabbit goes near the grass, and the fox is not able to get a rabbit and die.
The Dasies. The numbers arise not from the petals of the plant but for all sorts of mathematical regularities or any biological objects that can be counted. They begin in a so-called Fibonacci series where the number is the sum of two numbers preceding it.
According to Leonardo Fibonacci in the year 1200s, Leonardo Fibonacci discovered the Fibonacci number when he theorized the problem of the massive growth of rabbits. Because of the Fibonacci numbers, it gave more connection to mathematics and genetics and how this number can be seen anywhere in nature. Most mathematicians find the Fibonacci numbers as fascinating and beautiful as they are. Divergence angle. This is an angle found in the spiral position of a primordia. Based on the study by Stepan Duwadi and Yves Coder, they explain that each successive primordial spiral angle is equivalent to 137.5 degrees. This is done through dividing two consecutive Fibonacci numbers and multiplying it by 360 degrees. The golden number, the consecutive ratio between Fibonacci numbers gets closer and closer to the number 0.618034. For example, 34 divided by 55 is equals to 0.6182, which is significantly closer. This limit of this value is square root of 5 minus 1 divided by 2, or the golden number. This relates to the primordia as the angle between the successive primordia is the golden angle of 360 times 1 minus the golden number equal 137.5 degrees. This is the perfect primordial spiral that consists of the golden angle arranged in a spiral position. Conclusion. These three case studies tackle different topics involving geometry, dynamics, and the symmetry of the natures of objects. These studies gave an explanation as to how humans have perceived nature in a mathematical way, while genetics explained that these types of occurrence happen because of genetic events and have no way of fixation. Mathematicians believe that a more components determines the surroundings in a mathematical way while expressed interestingly and beautifully.